We're now going to talk about the common ForkJoin pool. And I've described it a little bit earlier when we talked about parallel streams, because that's what parallel streams uses. But now we're going to go into it in more detail, and we'll describe how it can be programmed effectively to allow it to shrink and grow, or grow and shrink, rather. So the common ForkJoin pool is a static singleton that's always available and appropriate for most parallel programs. Not all, but most. And oops, for some reason that's grayed out. This pool is used by any ForkJoin task that's not submitted to a specific pool within a process. So it's the default, the common ForkJoin pool. And the reason why we have it is to optimize resource utilization, since it's aware of what all the other cores are doing, because they're all working off this common ForkJoin pool. And so that allows us to be able to do a better job of reusing the threads and recycling them and reducing overall utilization. This is a very common pattern you see used over and over again in many different programming languages, runtime environments, operating systems, business environments. So this sort of local versus global trade-off is a very consistent theme. So a good example, naturally, would be the Java heap, the free store that Java has. So Java tries to do garbage collection. So it really doesn't want you managing memory locally out of some private cache. It wants you to use the global heap, because then it can do a better job of memory management and garbage collection. There are some times when that isn't the right thing to do, but that's kind of the idea. We deal with these things all the time in practice. For example, at Vanderbilt, we go back and forth between centralizing our accounting and funding models. Sometimes it's owned by the central administration. Sometimes it's owned by the schools and colleges. Likewise, our IT group here at Vanderbilt. Sometimes over the past, each school or each department had their own IT group. Right now, it's centralized into VUIT. And things go back and forth. This is just the way things work in general. Usually what happens is you centralize things for cost efficiency's sake, and then people get pissed off because the units at the edge are not happy with the response time because the central group is perceived as out of touch. So then they decentralize everything, and then people at the edges are happy for a while, but then it becomes much more expensive because you have to duplicate all this effort. You can't have common career paths and so on. So the world goes back and forth between centralized and decentralized architectures at many different layers and levels in computing and beyond. The common ForkJoin pool, as we've said many times, is also used by the Java Parallel Streams framework. So, as I mentioned before, it provides a facade for all the gobbledygook that we're going to talk about in detail. Now, here's an interesting little factoid. By default, the common ForkJoin pool has one less thread than the number of cores. So, on my quad-core hyper-threaded processor, available processors returns 8. And as you can see, the common pool is going to take 8 minus 1. So it'll be a total of 7 in the common pool, always one less the number of cores. And if you were to make this call, say ForkJoin pool.get common pool parallelism, it would come back with 7. So it would say there are 7 worker threads in this common ForkJoin pool. And the reason for that is that the invoking thread, whoever is going to be using the common ForkJoin pool, is also borrowed and used along with all the other elements in the common ForkJoin pool. So it's always number of cores minus 1, and then whoever the calling thread is, who invokes or whatever, that thread is also used. So you end up with the number of cores by default. However, as we've talked about before, and we'll go into more detail now, the default number of threads in the ForkJoin pool may be inadequate, may not work for what you need. And the problems occur when you have blocking operations that are blocking, like for I/O, with threads in the common ForkJoin pool. And so a simple example, let's say we have 4 threads or whatever. We're going to end up with, say, 10 images that we're trying to download, and those images will end up it'll end up underutilizing the processor, the multi-core processor, because after 4 images block, nothing else can happen until they finish, but there's other threads, there are other images that could be started to be downloaded if only we had threads to have them block. So it's often a problem if you end up with too few threads in the ForkJoin pool. So therefore, we want the ForkJoin common pool to be expanded and contracted programmatically. You can make it bigger, you can make it smaller, and so on. And there's a couple ways to do this. One way to do this is to set a property, which is called java.util.concurrent.forkjoinpool.common.parallelism, set that to some value, like, say, 10. The hard part here is it's difficult to estimate in advance the number of threads you should have. You sort of know for a particular application, I'm only going to have 10 images at a time I'm going to download. But in general, you don't really necessarily know how many things your users want you to do. So that may be overly limited. And the other downside with this, as we've talked about before, is that this property affects all the usages of ForkJoin pools in the process. So if you set this thing, then everybody's going to have to end up using it who's using the common ForkJoin pool. Therefore, we may want to do something that's more dynamic, more automatic, to be able to increase and reduce the ForkJoin pool size in an adaptive way or a dynamic way. And the way you do that is by using something called a ManageBlocker. And as we'll see, a ManageBlocker is an interface that gives you a couple of really simple methods that the common ForkJoin pool framework can apply to decide whether to expand and ultimately later contract the number of threads in the common ForkJoin pool, worker pool. And so what it'll do is that the ManageBlocker interface can temporarily add worker threads to the common ForkJoin pool. Kind of like, adding seasonal workers to Walmart or Amazon during the holiday season or whatnot. And this is particularly useful when tasks block on I/O or other synchronizers, because you don't have to try to guess what the program will do. It simply does what it does, and then the framework ferrets out what's going on and responds accordingly. Keep in mind that ManageBlocker can only be used with the common ForkJoin pool. You can't use it with any other ForkJoin pool that you create yourself in a custom way. Only the common ForkJoin pool can be used this way. And we're going to talk a little bit later about how to apply the ManageBlocker interface, and we're going to wrap it up with a really cool little helper class, which will make it easy to do this without having to know a lot of low-level details. It'll use other Java 8 features like suppliers and so on in order to simplify the behavior. The other cool thing about having ManageBlockers used to expand the size of the threads in the common ForkJoin pool is that the ForkJoin pool is programmed to detect when threads are not used for long periods of time and will automatically reclaim them and reinstate them later. So that's a quick overview of the common ForkJoin pool. What we'll do in a second is start to talk about how you program it.